So today we're going to focus on what's called the integral test for determining whether a series converges or diverges. Now let's set up the context of why we are introducing this integral test in the first place. So if you remember so far in our story of series convergence and divergence tests, we really have two tests so far at our disposal. We have the so-called test for divergence, and we have the so-called geometric series test. Now, both of these methods for determining whether a series converges or diverges are rather limited in scope, unfortunately. So for example, the test for divergence, it can't tell us whether a series actually converges. For that matter, it doesn't tell us whether a series always diverges, or for that matter. It just will, if a series fails the test for divergence, it's automatically divergent, but it doesn't catch every divergent series. On the other hand, something like the geometric series test is really great, as we just saw in the past couple days, but it only works for series that have a very restricted form. The series where we have the form some number times another number raised to the n-1. If the series is not in that form, it's not a geometric series, so we can't apply the geometric series test. So this is where we're bringing in our so-called integral test. And this will help us determine whether a series converges or diverges for a much broader class of series that are out there. So that's basically why we are introducing the integral test today, to help us determine convergence or divergence for a much broader class of infinite series. Now, the big thing to note from the integral test right away is this places the question of convergence or divergence onto an associated improper integral. So today we're going to be doing or computing a bunch of improper integrals to help us out figuring out whether a series converges or diverges. The other thing to note about the integral test is a function must satisfy three criteria in order to use it. So let's set up an example now. So if we're considering a series like the following, from n equals 1 to infinity, say the series n times e to the minus n. Well, this series is not a geometric series. You can go through that test. This series will pass the test for divergence. So at this junction, the only thing we can try to use for this series is this so-called integral test. Now, what we are going to do in the first step of the integral test, though, is we need to make sure we're actually allowed to use it. So we take our series function, this n e to the minus n, and we think about basically a continuous kind of counterpart for this, where we think of this as a function f of x equaling x e to the minus x. So you can see the similarities between our series function and how we're getting that function f of x. And now we're thinking of this function f of x on an interval of x values from 1 to infinity. And you'll note for our series function, our series is going from 1 all the way towards infinity as well. So the kind of buy-in allowing us to do the integral test is this function must satisfy three things. This function f of x, in order to apply the integral test, must be positive, it must be continuous, and the function also must be decreasing. If those three things happen, then we're going to see we're allowed to apply the integral test to it. So again, the big idea for today is we're getting this new convergence divergence test called the integral test, which will allow us to determine whether a broader class or broader range of series converge or diverge. In particular today, we're going to talk about a series called the p-series, in which we'll see when the p-series converges or diverges. But that's kind of the big idea of what we're going to get into today.